Now, the Miller indices, another important concept. So, Miller indices is there for direction as well as planes. So, let us first discuss direction, Miller indices of direction. So, A B is a direction, A B is a direction. Again I have taken that same unit cell, the sodium chloride unit cell, just as an example, and I am thinking of a direction A to B. For defining the Miller indices, two important things are there. First, where you will choose the origin, you have to choose an origin, and x, y and z, one thing is defined, that because we have to work in crystallographic coordinate system, and axes of the crystallographic coordinate system has to be parallel to the edges of the unit cell that we have seen. Of the unit cell. An origin at a corner, which is a lattice point. However, still there is lot of degrees of freedom left for me. First of all, this unit cell has 8 corners. So, I can choose any of the 8 corners as my origin, and then from each corner 3 edges of the unit cell emerge, 3 edges of unit cell meet at each corner. Which one I call x, y and z is again my choice. What I am calling x, you may be calling y, and we may fight unnecessarily. So, we have to be very clear, there should be a clarity of which corner we have selected as the unit cell and which edges we are calling x, y and z. So, for Miller indices of direction, one of the convenient, although not necessary, but one of the convenient choice of origin is to choose the origin on the direction itself at one point of the direction. So, for A B I will choose the origin at A, and then for this problem we have once for all decided that my x axis will be pointing this way, y axis will be pointing this way and z axis will be pointing this way as shown here on the side. Since the freedom for choosing the origin was there, that is why I showed the axes away from the unit cell and not embedded on the unit cell, because I do not want to give preference to any corner. Wherever I draw this on any corner, so that corner becomes a special as a chosen origin, the chosen one, but I do not want to initially give that status of the chosen one to any. So, when I come to figure out A B direction, then I choose A as origin. So, if I choose A as origin and then my direction A B is along A. So, the vector A B is 1 O O. Okay. It is A O if you want, but we have already defined the fractional coordinate. So, we will divide by A. So, that becomes 1 0. Okay. The components of the vector in the direction itself is the Miller indices. So, we have found the Miller indices of A B. So, this is the Miller indices of A B. So, it is just a vector. Although it is a vector, when we say its Miller indices of direction, we imagine that we are talking of this entire direction. Vector has a fixed length. So, I could have chosen any vector along this length, but I will get the same Miller indices. How? If I choose twice the vector, then that will become 2 0 0. So, I introduce one more step in deciding the Miller indices, that if you can divide by a common number, you are allowed to do. So, divide by some common number to reduce it to smallest numbers. So, as soon as I see 2 0 0, I divide it by 2 to get 1 0 0. So, even if I had selected a longer vector, or if I had selected a shorter vector half 0 0, then I am allowed to multiply by some common number to get 1 0 0. So, 1 0 0, half 0 0 and 2 0 0 in terms of vector, if we are thinking in terms of vector, and sometimes we want to think in terms of vector. So, there is nothing wrong, then they are 3 different vectors, all in the same direction, but of different lengths. But if I am thinking in terms of Miller indices, I will reduce all of them to 1 0 0 and say I am talking of the 1 0 0 direction. So, 1 0 0 direction will always be the x direction, will always be the direction along the A of your unit cell. So, let us now look at some other direction AG direction. So, what will you get? Yeah. AG, yeah, 1 1 0, 1 along A, 1 along B. So, essentially the in terms of vector. So, see if I write it as a vector AG, so I will write 1 times A plus 1 times B plus 0 times C. So, that is the vector. In terms of coordinate, it becomes A, B and 0 in terms of coordinate. But then in Miller indices we use the fractional coordinate. So, we will divide first one by A, second one by B and third one by C. So, I get 1 1 0. So, you can see although we are calling it 1 1 0, the two ones are not equivalent. The second one is representing a length B. Here in NaCl unit, since it is cubic, A and B lengthwise also are equal, but even if they were unequal, this face diagonal direction will always be 1 1 0, but the second one will be representing B step of a different length and the first one A step. Which one we should do now? GF. What is GF? So, what is your chosen origin now? So, it is nice to choose the origin here now. We were working with A because we were having AB and AG, but now we have GF. So, we shift, we bring our origin here, and if we bring our origin here and choose when you shift in one problem, initially you were free to choose your x, y and z also. I told you which one you call x, which one you call y, you are free. But if I am doing one exercise, one problem, then once chosen the x, y, z orientation, when I shift the origin for my convenience, I do not flip the x, y, z. So, x, y, z I have to keep the same. So, then I have to going from A to F, I have to go -1 along x, -1 along y and 1 along z. So, -1, -1, 1, and in crystallographers decide to write minus on the top as bar. So, that is the Miller indices of direction.